Welcome back to differential equations. In this video, we're going to be looking at two methods of solving differential equations that you should have seen in your previous study of calculus. The first one is the method of direct integration, which we'll get through very quickly. It's unfortunately very rarely useful. And the second one, the title here, the method of separation of variables. Let me get my head out of the way and let's dive right in. The method of direct integration will apply to first order differential equations and also to higher order differential equations. The key aspect of a directly integrable differential equation is that you have some derivative. Let's look at a second derivative, say y double prime of t on the right-hand side, or on the left-hand side, and then on the right-hand side, you have a function that contains t but not y or any of the other derivatives. So for example, if I have y double prime of t is equal to 2t plus 1, then if I integrate on both sides of the equation, the fundamental theorem of calculus tells us that the integral of the derivative of a function is the function you started with. So extending that, the integral of the second derivative of a function is the first derivative of the function. And then on the right-hand side, I chose a relatively simple polynomial. But of course, whenever you perform integration, there is always an arbitrary constant of integration that appears. Technically, there should be an arbitrary constant on both sides of this equation, but here is where we get really creative with our arbitrary constants. If I add some constant a on the left-hand side and some other constant b on the right-hand side, I can rearrange the equation by subtracting a. So I get y prime of t is equal to t squared plus t plus b minus a. If I can pick b to be anything I want it to be, and I can pick a to be anything I want it to be, the only thing that really matters is the difference between them. Call that c. We just created a new arbitrary constant to reduce the complexity of the arbitrary constants. Although we are still going to have some more work to do, so instead of calling this c, I'm going to call it c sub 1, because we want to find y, and the next step is going to involve doing more integration. And so we're going to have another arbitrary constant show up, and in this case, it is going to be different, so having a different letter is important. It's a good habit to use subscripts instead of using different letters because you might run out of letters. But we do the same process again. We integrate y prime of t with respect to t, and we integrate t squared plus t plus c1 with respect to t, and we get y of t is equal to 1/3 t cubed plus 1/2 t squared plus c1 times t plus our new arbitrary constant of integration, c2. And notice because of that t, we can't combine these two arbitrary constants, and we end up with an expression that has two arbitrary constants. That makes sense based on things we've talked about previously with initial value problems. This was a second order differential equation. It has a double prime in it. And so our solution has two arbitrary constants, and we will need two initial conditions in order to find a particular solution. We could continue from there. I don't find that part of the process to be all that interesting. So instead, let's move onward to the meat of today's lesson, the separation of variables. Separation of variables is a technique that takes advantage of bad habits that physicists love to try to introduce into mathematics. Not every differential equation is separable, but every differential equation which is separable is a first order differential equation. And I'm going to write the derivative using the fraction notation dy dt instead of using a y prime. But we need to have a dy dt on one side of the equation, and on the other side of the equation, we need to have some mess going on. So as an example, let's take a look at something relatively simple. Dy dt is equal to t squared times y. In calculus, I stressed many times that even though this looks like a fraction, it is not a fraction. This is why so many mathematicians hate differential equations. It's not a fraction, but let's pretend it is and see what happens. All right, I'm going to go through this particular problem twice. The first time I'm going to do things very carefully. The second time I'm going to play fast and loose with things, and you'll see why playing fast and loose with things is really going to make our lives a lot easier. Right. I can rearrange this equation just a little bit and call it 1 over y times dy dt. And then I have t squared on the right-hand side. Then I can try to integrate both sides of this equation with respect to t. On the left-hand side, I have a very obvious u substitution that I can use. If I let u equal y, then du is dy. And in fact, that's what I have. Right? dy is equal to y prime of t times dt. That's y prime of t, that's dt. That's all I've done here. What it looks like I've done here is cancel out the dt's. I did not. Let me stress that again. I did not. dy dt is not a fraction. I can't do that. I can't cancel out the dt's. But let's pretend I can anyway. It makes it a lot easier to think about. And in fact, I can take that one step further. This is why it's called separation of variables. Going back all the way to the beginning, if I pretend that dy over dt is a fraction with differentials in it, then I could, in theory, multiply both sides of that equation by dt. And then divide both sides of the equation by y. And that becomes a lot more clear as to what I'm trying to do. Again, I want to stress that the stuff I wrote in yellow is not allowed in mathematics. But if you take a course in physics or engineering, that's how they're going to write it out. And to be perfectly honest, it makes more sense. Because let's take a look at this. I have separated my variables, right? In this second line, my equation has y and only y on the left-hand side. It has t and only t on the right-hand side. I have separated the y's and the t's. That's how this process got the name separation of variables. You can't always do this. It doesn't always work. But when it does, it is incredibly powerful. Either way, we get to the same integral, so we can continue from here in either case. The integral of dy over y is the natural log of the absolute value of y. The integral of t squared dt is 1/3 t cubed plus some arbitrary constant of integration. Continuing from here, once again, I'm going to take the time to be careful about the next couple of steps, but you're going to see that there's a pattern and you can exploit the pattern and you can save yourself a lot of headache. In physics and engineering courses where this comes up, people skip from here to the end without writing out any of the intermediate steps because it looks exactly the same every single time. But what we're going to do is use the property of exponentials as the inverse of logarithms. If the natural log of something is equal to this mess, then that means that the original something, actually, let me copy that onto the clean slide so that I can get away from the page break. Right. If I have that, then that means that the absolute value of y itself is e raised to the power of all of that stuff. Now from here, I'm going to do a couple of things. First of all, if the absolute value of y is equal to this thing, property of exponentials that you should be familiar with, e is a positive number. A positive number raised to any power is another positive number. So the right-hand side here is always positive, which is great because on the left-hand side, I have an absolute value. Y itself could be either positive or negative. So to extend out and talk about my family of functions, y itself is plus or minus e raised to the 1/3 t cubed plus c power. Next, I'm going to play around with properties of exponents. Adding in the exponents is the same thing as multiplying like bases. Usually, when you've used this property in the past, you've gone in the other direction, and you've taken something like e to the c multiplied by e to the 1/3 t cubed, and you've rewritten it as e to the 1/3 t cubed plus c. But there's no reason we can't go in this direction. Then I'm going to take a look at this thing. Plus or minus e to the c power. C itself is any arbitrary constant. When I raise e to the c power, I can get any positive constant. I can't get 0, I can't get a negative number, but I can pick a value of c to give me any positive number I want. Then I take the positive or negative branch from that choice, giving me any positive number or any negative number I want. The only thing I can't get is 0. And that makes sense. If I scroll way back up to where I started doing all of this, my very first step was to divide both sides of the equation by y. If y is equal to 0, I can't do that. And so if y is equal to 0, everything falls apart. So I can't set this constant equal to 0 because it would cause everything to fall apart, but it can be any other number I want. So I invent a new constant, I'll call it A, and my solution, my general solution is y equals that constant A times e to the 1/3 t cubed. Separation of variables doesn't always quite work out this way, but very often when you're dealing with separation of variables, you're going to have a left-hand side that turns into dy over y like this. And so this process is going to play out very similarly. And we like to skip steps. Once we understand how this process is going to work, we would rather not have to write it out every single time. So as another example, let's take a look at the differential equation. 2 times t times y prime is equal to 5y. If I rewrite y prime as dy over dt, and notice that if I divide by y, I divide by 2t, and I multiply by dt, I can rewrite this as dy over y is equal to 5 dt over 2t. Those constants could have ended up anywhere in the expression and everything would work, but the closer I can get to dy over y on the left-hand side, the more I can rely on the pattern that I just developed. I'm going to integrate both sides. Integral of dy over y is the natural log of the absolute value of y, but I know that that absolute value is not going to do anything at the end, so I'm just going to write it as natural log of y. And I know that I'm going to be able to rewrite this using that same process I used before. If natural log of y is equal to all of this and I have a plus arbitrary constant, I know that y itself is going to be some new constant a times e raised to that same power, 5 halves natural log of t in this case. All right, so that's what I'm talking about when I say we want to use the tools that we have and we want to simplify things as much as possible. Right? We could have gone through and written out everything in detail. There's nothing wrong with it. But once you've seen it once and you know how it works, you can jump through. You don't have to write everything out again. Something math students are always clamoring for. So now that I get to tell you it, you get to cheer. I don't need you to write out every single step. You can jump ahead like this. Although, unlike in the last problem, in this problem, we're not quite done. Because in this problem, I've got an e and I've got a natural log. That means I can do a little bit more cleanup. Right? Properties of natural logs. R times natural log of x is natural log of x raised to the r power. So 5 halves natural log of t is the natural log of t to the 5 halves power. And the exponential and natural log are inverses of each other. So e raised to the natural log of something is that something. And the simplified solution to this differential equation is y equals a times t to the 5 halves power. If you're looking at all of this and thinking about e raised to powers and exponential models, you are exactly right in the correct direction. Something that you should have seen in calculus. I don't want to talk about in depth, but it's worth referring to just a little bit. If you have a differential equation in the form y prime of t is equal to some constant k times y of t, then you have what we call an exponential growth model. It is an incredibly simple differential equation to solve. I solved it for my calculus students. It separates to dy over y is equal to k times dt, which means that the natural log of y is equal to kt plus c. And using the same process we've been using, we get y equals a times e to the kt. Right? There's the exponential growth formula that you are accustomed to. All right. I don't want to deal with exponential growth in this course. Exponential growth is a calculus topic that you should have already seen. But I like to mention it to start thinking about what it's saying and how we can use that to extend things. Exponential growth says that the rate at which something changes is proportional to the amount of the thing you have. And that's something that is very common in the world, right? Population growth, certainly, but also some places you might not expect. Modifying that ever so slightly. If you have an object on a spring, the force that the spring is pulling the object back to the origin is proportional to how far away the spring has been pulled. Right? It's not quite a linear proportion between distance and force, but it is a proportion there. And so that's something we can start working with and we can start using to build up differential equations that are going to look kind of similar to this. And if they look kind of similar to this, then our solutions should look kind of similar to that. And it won't be much of a surprise as we go through and we start solving more differential equations. Exponential functions are going to be everywhere. In fact, spoilers for something that's several videos ahead, one of my favorite tools for solving a differential equation is let's assume that the solutions are exponential functions and then see if we can figure out which exponential functions they are from there. For right now, though, we're sticking with separable differential equations. So let's end with one for you to try. I have here the differential equation y prime plus 2yt equals 0. And this is going to be an initial value problem, which means I'm also going to give you an initial condition. Y of 0 equals 1 is a relatively simple initial condition. And I'd like you to take a couple of minutes and see what you can do about solving the initial value problem. I haven't looked at an example that combines those two skills, but we have looked at how to solve a differential equation. And we've looked previously at if you have a solution of differential equations, how can you use that to solve the initial value problem? I'm asking you to put those two things together. It's a two-step process. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.